started with the next sections. It's okay, Renate, that we agreed that I take over now, right?
It was my assumption. Yeah.
Yes, good.
Thanks.
All right, so our next speaker is Daniel Brown. Just a couple of words. Daniel is from the University of Adelaide, but he's originally from the UK, if I understand this correctly. He's very much on the experimental side of things, so completely different to what I was talking about. But that's the nice thing about the topic of gravitational waves, because everybody is really involved. All kinds of different disciplines are involved in this. That's really interesting. So as I said, Dan is originally from the UK. He's in experiments. He's an expert on the detectors in the interferometric detectors. He's the chair of the LIGO Scientific Cooperation Advanced Interferometer Working Group, and he's also involved as the co-chair in the Einstein Telescope Low Frequency Design and Control Scheme. So he will explain to us what that all means, and so Dan, please get started.
Okay, thank you for having me here today. Let's get my screen shared. Is that right screen coming through okay?
Yes.
Brilliant. Okay, so yeah, thank you very much for having me here today. It's very unfortunate we couldn't obviously do this all in person, but hopefully I can, without waving my arms around too much in front of you, trying to explain how gravitational wave detectors work. Maybe we can try and get it across on Zoom instead. So I'm from the University of Adelaide. I've been a postdoc here for the last sort of five or so years, and I work a lot on sort of the advanced detector era, and also commissioning and working at some of the LIGO sites, trying to get the detectors up and running today to give all the data analysis people plenty of exciting new data to work with. So we've been asked today just to talk a bit about sort of Earth-based gravitational wave detectors. There's quite a broad spectrum of different types of Earth-based detectors, but I'll be predominantly focused on sort of the long baseline interferometric type detectors. By all means, if you do want to drop me any questions about anything experimental related, my email's up here, daniel.d.brown@adelaide.edu.au. So feel free to email me any questions that you might have about the detectors and such. So I guess just to start off, last year was kind of an exciting year as an experimentalist, seeing the James Webb Telescope go up, and it kind of reminds you of the how much better life can be when you actually end up making such these better detectors that have orders of magnitude of improvement over what had existed before. And so, for example, on here you can see on the left we can see the sort of early pictures from the James Webb Telescope compared to what Hubble could see, and you could just see order of magnitude better image. We can see way past all this noise, and we can really start picking out some really cool and interesting stuff about how the universe works. And so, of course, the same applies really for gravitational wave detectors. Advanced LIGO, Virgo and such, I mean, they're really just the first set of detectors that are really designed just to detect gravitational waves, which obviously only happened relatively recently. Here, for example, is a simulation of what we would have expected the GW 150914, so the first big black hole binary signal that we measured at LIGO. What this looks like, for example, where we measured that signal today when the LIGO A+ upgrade is done, which won't be done for another couple of years, versus what we'd actually get with Cosmic Explorer, which is much further afield upgrade to the detectors, order of magnitude improvement way across the frequency band. And so you can see instantly here just how much of an improvement you see from this just noisy kind of choppy signal here, even just from the LIGO A+ detectors, which is already a decent improvement on what advanced LIGO saw many years ago. Once we get to this Cosmic Explorer level, we're really seeing just nearly perfect signals, which obviously opens up a lot of doors and avenues for people to work through. So yeah, just a bit of kind of motivation for why we should be interested in this type of stuff and why we should support making bigger and better detectors. So obviously we have a bunch of detectors all around the world. LIGO They've got two in the US, LIGO Hanford, LIGO Livingston, one up near the Canadian border, one down in the south. There's also Virgo, which is slightly shorter, but in Italy, it's a 3 kilometer long detector. LIGO is about 4 kilometers. There's a shorter, more prototypish type detector called Geo 600. Pioneered a lot of things we're probably using, like squeezed light, another kind of control system schemes. There's also another one in Japan called Kagra. This is another 3 kilometer detector, cryogenic. It's got a lot of other cool features, but it's also built inside a mountain, which is quite fun to try and isolate it from a lot of seismic and environmental impacts. So there's quite a lot going around the world. We also have LIGO India, which is kind of an in progress sort of build or extension of the LIGO detectors. LIGO actually had 3 detectors originally. So we actually have the parts lying around for a whole other detector. And the idea is that LIGO India will eventually get to the point where they could acquire the land and build another 4 kilometer long detector. So we'll have another long baseline detector around, which will then allow us to do, for example, other upgrades for things like the LIGO Hanford Livingston detector without everything being down, for example. So let's talk a little bit about how they actually work in practice. A lot of this will just be the idea on sort of how we work from the sort of optical sense. And so at their core, really, gravitational wave detectors are what we call Michelson interferometers. And so these are essentially, as you can see in this animation down here, we have a laser component, we have a beam splitter, and we have what we would call these 2 end mirrors. And these 2 long things are the arms of the detector. And so these big long arms are the 4 kilometer aspects. And so when a gravitational wave comes in, as I'm sure you probably heard in this morning's lectures, these will stretch and distort space and time. And it's kind of a quadrupole wave. So as we stretch one arm, we squash the other. And so ideally, when the polarization is on signal perfectly aligned to the detector, we find that the arms of the detector end up just changing in length. And so we get this small, what we call differential change in the lengths of these 2 arms. And we can observe this small change by flashes of light that appear out of what we call this output detector. So you can see that for big changes, this flashes all the way from dark to bright as we go all the way through one of these dark and bright sort of waves. We call this a fringe. And it's these small fluctuations that we're essentially taking the phase change that's induced from a gravitational wave stretching and squashing time and changing that into a flash of light that we can measure with just a photodiode. So of course, this animation here is showing something that's incredibly large. They're never that large in reality. The strain, or this sort of change in length over the length, it's a unitless number here for a very loud sort of event. You're really talking about something that's like 10 to the minus 20 or something. So even over the length of 4 kilometers, this is a very small change in the length of the arms. Nothing that you'd ever be able to see with your eyes, such as this. So if we could just do a quick back of the envelope calculation, say like how much light, how much signal do we actually even get for any of this type of signal. So you can imagine we have a Michelson interferometer. We've got these 4 kilometer arms. We've got a 35 watt laser, which is about standard for the type of lasers that we kind of need for gravitational wave detector we can buy. And then we've got a 10 to the minus 21 sort of strain applied. So how many photons do we end up seeing? And so you can just do a rough calculation. We've got a certain amount of power. We have to see the energy in the photon. And so you can work out that roughly there's probably about 2 times 10 to the 20 photons per second sort of in the arm being generated by the gravitational wave side. And so, of course, so in the actual arm, sorry, from the laser. And so if we actually look at the fraction of those that would sort of interact with the gravitational wave and come out of the dark port, the amount of power coming out is whatever the power coming in times some sort of scale, sinusoidal scaling factor here, depending on where we're operating on this fringe pattern. And if we actually work this out, it's actually about half a photon per second, which doesn't sound like a big signal, and that's because it's not. We're not really in the business of counting photons. It's not a great way to measure gravitational wave signals. And so we're really running into a problem here that, I mean, how do we get more? How do we get more photons? We need far more than this to actually detect something and make a decent signal. And so from this just rough calculation here, you can already see there's sort of 2 factors that we can kind of work with here. We can either increase the power a lot, or we can increase the length of the arms. And so that sort of scales this kind of fringing effect here. And so there's only so long you can make an arm. LIGO, for example, is 4 kilometers. You can't really keep making it like hundreds of times longer because you just start running out of Earth to actually put it on. And there's just only so many places on the planet that have that much empty space that you can work with. And so we're really kind of limited for something like when you fix the length. Really, the key is you just need far more laser power. And so the story of why LIGO kind of looks the way LIGO does, and why the things in Virgo does, and why the way we build them is all really just to try and get as much optical power as we possibly can without having to build a huge laser. And so thinking about photons isn't the most useful way to do it. It's just kind of a nice number to just kind of illustrate the fact that it's very small. It's a very small amount of signal. And as you can imagine, it's very easy to get a few extra photons somewhere that's going to sort of hide it. And so what's really the crucial factor here that we want to know, or the term we want to know, is really this sort of signal to noise ratio. Also how much noise there is present in our system that kind of looks like a gravitational wave signal. And so for those of you that's not seen these kind of strain sensitivity plots before, whenever you look at LIGO data, like the LIGO instrument type stuff, or you hear someone talk about things about LIGO or gravitational wave related, you often see these types of plots. And so on the bottom here, on the x-axis, we have the frequency of the gravitational wave signal. And obviously the amount, depending on what frequency there is, depends on whether we've got more signal or less signal or sensitivity. And then on the y-axis here, we've got our strain sensitivity. So it's a power spectral density. So how much we can actually, so basically how sensitive our detector is at a particular frequency. What's the weakest gravitational wave that we could see? What's our limit? And so before we're kind of talking about just photons, they're just like shot noise, sort of Poissonian statistic. We've just got a certain number of photons, there's just a counting error there, and that kind of gives us this very baseline limit. It's actually a very fundamental limit to how the detectors, how good you can actually make the detectors. And you can see that in this kind of blue line here. It's really just the fact there's just a limited number of photons that we're getting out of there. And the more we increase it, the better our signal to noise ratio there improves. And so you can see it's kind of relatively flat in this kind of frequency band, sort of what we call bandwidth of the detector, and then it actually gets a lot worse. And so idea is, so here we want the strain sensitivity to be lower is the better, lower is better, and so if it goes up, that's bad. And so this peak here is actually where the gravitational wave signal ends up cancelling itself out in the round trip of the arm. And so the phase induces, it kind of subtracts away again. So it cancels itself out. And so you often see that the sensitivity of the detector kind of gets worse as you go to higher frequencies, and that's essentially just running out of bandwidth for the detector to operate at. Then there are also a myriad of noises. There's more noise than we want. They come from many different sources, some of which we'll talk about in slides for you later. For example, here it's just what the frequency noise of the laser is. And so if you have some imperfect laser, which they do, there's no such thing as perfect, this will eventually look a bit like a gravitational wave signal at some point. Some of this frequency noise gets down to this photodiode and it makes itself look like a gravitational wave signal. And so that puts a limit there. And so you can already see this kind of, if you used to have seen some of these noise sort of budgets before from LIGO, you see you've already come across this kind of very bucket looking shape. There's lots of low frequency stuff that always gets worse towards lower frequencies. We have shot noise and thermal noise things in the middle, and then everything kind of gets worse as we run out of bandwidth as we go higher up. So how do we get more power essentially? So the big aim is we just can't build a bigger laser. If we try and build a bigger laser, typically we can make kilowatt lasers, for example, but they typically don't have a very good frequency noise or intensity noise. And so there's a bit of a trade-off, a technical trade-off of how good you can actually make a laser. And so really the story of how LIGO looks the way it looks is the sort of story of the optical cavity. And so for those who have not come across what we call Fabry Pro cavities before, these are essentially just a way to what we call resonate light. And so we have two mirrors in its simplest form. We have a laser, and we inject some of this laser light through this input mirror, which might have a reflectivity of, say, 90%, so only lets 10% through. An end mirror that's nearly 100% reflective. And so as this laser just continuously injecting more and more light, this laser light, if we can control the length of this cavity precisely, builds up and up and up. So we get this constructive interference. And so the idea is that what we want to do is we inject this light in through the input mirror, it gets launched in, and it constructively interferes and interacts. So we essentially make a light standing wave between these two mirrors. And so as this light circulates around, it actually builds up. You can actually get quite large magnification factors inside the arm cavity, and then little bits of this leak out. They get lost from things like scatter light, or there might be some absorption in the optical coating. Some of that light gets turned into heat, for example, scatters away due to surface roughness. And there's just a limit because of how high we can make that, because we have to be able to get the light in there in the first place. So there's always some loss. We can't get an infinite amount, for example. And so there's various properties with an optical cavity that are useful to kind of keep in mind, just to try and understand how the detectors work. And so there is something called the free spectral range. And so this is the difference in sort of axial mode spacing between different wavelength frequencies of light that will resonate. Obviously, we can make one wavelength of light resonate, but we can also pick a slightly higher and lower one. So this is just limited by essentially the speed of light and the length of the cavity. And so there are an infinite number essentially of these optical resonances. And what we see here on this axis is the frequency of the light going in, and then the amount of gain that we have. So for example, if we inject the light in at the right frequency, we can actually get an optical gain here in this particular cavity with a transmission of about 5% on the input mirror of about a factor of 80. So you can imagine we've got this 35-watt laser that we've got around, so we can instantly just get more power somehow inside this cavity. If we can build a cavity like this, we get 80 times the amount, which is quite a lot. And so this frequency is also sort of degenerate as well, with the idea that it can also be the length of it, or the length of the cavity. So we can either change the frequency of the light to fit inside, make a standing wave inside the cavity, or for example, if we've got a very particular frequency of light, we can also adjust the length of that cavity to fit that particular standing wave. And these kind of resonances need to be controlled like on the nanometer scale. Things like LIGO actually need to be sort of controlled more on the femtometer scale. So you have to control the position, the microscopic positions of these mirrors relative to each other by incredible precision to actually make these resonances build up the way they do. Obviously, if it's moving around too much, this will degrade and would lose all this optical gain. And so the other part is round trip loss. Round trip loss really limits like how sort of good this optical gain can be. As you can see, if we increase the optical gain, we have less loss. We've got less transmission loss here. This peak gets narrower. So we have this what we call a gain bandwidth product. We can have a high gain, but we have to sort of sacrifice some of our bandwidth for that purpose, which is important later on when we start thinking about how we design detectors. So if we want more laser power, we have to have narrow bandwidth. We're taking all that stuff and squeezing it into a smaller frequency range. There are some terms here that you kind of might hear people talk about. There's what's called the finesse of the cavity, which is kind of a weird name. But essentially, it's just a measure of how narrow this peak is. So the less loss you have, the higher the finesse. You might people say, oh, the arm cavities of LIGO have a 400 finesse or something. And it's just kind of a nice number that people just kind of keep track of in their head for doing various calculations. And so if you want to go from finesse to example of how much gain that you get, it's then just 2 times that divided by pi. And so the first idea is what we might want to try is like, wow, we've got this optical cavity and we want more light interaction with the gravitational wave signal. So why don't we just stick cavities in the arms? And that's the first thing we can actually try. And this is what's called a Fabry Pro microsome. So one of the first sort of steps in this process. And the idea is we've got this main laser, we inject it in through the beam splitter, we split that light in half of it goes up to one arm, half goes to the other. This light, rather than just having 35 watts going in now, we can actually end up getting this gain factor of like several hundred per se, depending on the reflectivities we pick. And so we can dramatically increase the amount of signal or photons that would be interacting with that gravitational wave that are passing through. Because it's a differential in nature, the gravitational wave signal that comes in, what happens is, like the green light here shows, is the green gravitational wave signal is actually what we call a differential signal. So it doesn't go back towards the laser, but actually goes back towards its output photodiode where we can detect it. We actually run the detector so that the bulk of the light doesn't actually go down towards the output photodiode, it actually goes back towards the laser. This is what's called operating on a dark fringe. So we try and keep this port dark of as much light as we can. And so all this light ends up going back. So you can say, I'll reject 35 watts in, a few photons of that gets turned into a gravitational wave signal, a bunch of it gets like lost through scattering and absorption and various other things. But most of that laser light actually just goes straight back towards the laser, which seems like a waste. So what we can do is you put another mirror in and we can make another cavity. And so this is what's called the power cycling mirror, because what we're doing is we're taking the power that's essentially just wasted because we just send it in and it's reflected back. We take that light and we just send it back in again for another round trip. And so this power cycling mirror here actually creates another cavity between the power cycling mirror, the beam splitter, and these ITMs. So this one stands for, so I said this before, the ITMs are the input test masses, the ETMs are the end test masses. So this is the Y arm and the X arm. And so this power cycling mirror then ends up making an extra cavity here. And so you can actually start stacking these cavities together. And so now if we've got the gain of 1, which is like the gain of the power cycling, the PRC, times the input power, that tells us how much power is inside this central part of the interferometer. And then that gets magnified again by another factor inside the arms. And so the amazing aspect of LIGO is you can actually build this thing and control this thing. You can actually roughly get about nearly 6,000 or slightly more than 6,000 times more laser power. So now if we start thinking, oh, we can maybe make a 100-watt laser, we can now really start getting up to nearly a megawatt of arm power, sort of power actually stored in the arm. And there's no way that anyone will ever be able to make a megawatt laser just straight up that will be quiet enough. And so these cavities really allow us to build up a very high amount of power stored in the arms for interacting with the gravitational wave signal. And so there's kind of a trade-off here. Again, we start narrowing the bandwidth and various other things we'll come to in a minute. We also start running into a lot of thermal issues, because if you start trying to store too much optical power inside some of the substrates of these optics, you can imagine this is just big bits of glass, and you've got like kilowatts of light going through there. That glass gets hot, it deforms, it bends. And if it bends and distorts too much, LIGO is very sensitive, it doesn't like it, and then it can stop working. And so a lot of these gravitational wave detectors, there's a lot of trade-off and balancing between kind of how far we think we can push sort of the properties of some of the best glass in the world, the lowest absorptions, and how much power we think, well, how much power we can try and actually get into the detector for detecting a signal. And so we can kind of see roughly that here about this is this bandwidth problem that we're coming across now. And so we've got this black line up here, which is the of how much, this is what just the plain microsyn is, no Fabry Pro arm cavities, and then we can gradually add them. And so again, this is a strain sensitivity plot, and it shows you the kind of limit of how far we can get. And so with the black line, we can see we've got strain sensitivity about 10 to the minus 21, which is not very good. And really, we want to be really getting down to 10 to the minus 24, which is where LIGO is kind of aiming for at the moment. If we just add the arm cavities and such, we end up with the red ones. And so this again gives us a massive improvement, but you can see that we've drastically reduced our bandwidth. So we're really starting to lose signal now and sensitivity once we start getting into the kilohertz regions. And of course, depending on what astrophysics you're interested in, that might be a good trade-off. If you're not interested in what's happening at 10 kilohertz, there's no point being sensitive there. You might as well try and narrow that bandwidth and really concentrate in the frequencies that you're interested in. And then you can add in and you can add in the power cycling cavities and get even more power in the arms, and you can see you can dig down even further and start really dipping down into these sort of 100 hertz region, which is exactly where LIGO is kind of aiming for. And as you can see, we get this very sort of a common looking bucket type feature for the detectors. So the last piece of this puzzle is what's called the signal recycling cavity, which is an interesting one, because what it's essentially we're doing is we're doing the same trick that we did with the light that we wasted, that's being directly reflected from the arm cavities. But instead, what we're doing is we're taking the gravitational wave signal and we say, wow, if we want more signal, why don't we just recycle it again? Why don't we just send those photons back in and start having them interact with the gravitational wave signal for longer? And so, and this works. It provides a sort of a lever that we can twist and turn on the detector, which actually kind of lets us tune the shape of the response of the detector, a bit like how you tune a radio to be more sensitive at one frequency or pick up signals in different bands and stuff. And so as we can control this sort of microscopic position of this mirror here, we can decide how much of signal we can send back in and how much we'll let out. And the nice thing is this only affects differential part, because we've controlled this dark port, this count of the interferometer, so that none of this like high megawatt powers are actually getting down here. And so that megawatt power is not being affected by what we do with this signal recycling mirror. So really, we're just purely tuning and changing the response of the detector. And so this can give us quite sort of drastic improvements depending on where we operate it. Now there's what's called signal recycling, which is where we're really taking that signal and we're sending it again, and we're sending it back in to interact with the gravitational wave. And this gives us a very, as again before, we operate a cavity on resonance to recycle it and get maximal gain. We end up sacrificing bandwidth. And so we get more gain, less bandwidth. And that's exactly what we can see, for example, in this red plot, in this red trace here with signal recycling. What we've done, we've got rid of lots of bandwidth here. And we've really decided to focus really far in on just over, 80 hertz. And so if you're really interested in the signal at 80 hertz, this is a good thing to do. But of course, if you're interested in more the broad band sort of gravitational wave signals in spirals and all the rest of it, then this is not the best, because you sacrifice a lot of sensitivity everywhere else. That's what's called signal recycling, the red one. What we actually do is a thing called resonant sideband extraction. And so this counterintuitively is actually where we anti-resonate the signal. So we actually stop the signal resonating as much as it should do. And so this is kind of cool because what you can actually do there is you actually completely broaden the bucket of the detector. And so you end up with this blue curve here relative to the black one. And so now we can see if we pick the position of this signal recycling mirror on just the right point, we end up gaining these huge factors all across the band to get a much wider bandwidth detector. And so advanced light gun and Virgo kind of played with the idea of doing this. You could swap between the blue and the red curve here. It's actually very difficult to do experimentally. You can't just take this mirror and just shove it into a new position because the whole thing just falls apart. You can't actually control it and make it work that way. And so now we don't predominantly just operate in this kind of blue area here, the blue region. So resonant sideband extraction, maximum bandwidth, detect as much signal as we can, average across the board. And so this is quite nice because, as we saw before, what we were doing when we were trying to increase the power is we're constantly, as we put more and more higher finesse cavities in there to try and get more and more optical power, we're kind of naturally limiting our bandwidth. But this resonant sideband extraction is a beautiful technique that we can actually have those huge amounts of optical power, but then we can kind of cheat and say afterwards, it's like, oh, we'll actually just make the signal resonate less so we get more bandwidth. And so what we do is we try and just sort of balance off this fact. We try and get more optical power in there and also use resonant sideband extraction to try and sort of broaden out the response of the detector again, so we don't end up with this very narrow band response. So of course, this gets, as I was sort of alluding to before, there's this aspect of this control. So this is something you could talk about on a whole lecture series, but trying to actually control all these various mirrors. All these mirrors have to be precisely sort of positioned within femtometers of each other. They have to be controlled for sort of days or weeks on end. They have to survive earthquakes coming in, people bumping into it, sort of things switching on and off. It has to be incredibly robust so that we're constantly up and observing all the time. And so to actually make something that works like this over 4 kilometers is an incredible feat of engineering technology, and requires a vast array of various different sensors and actuators and all sorts of things to actually keep this detector operating perfectly all the time. And so just broadly speaking, the way that we actually do this is we pick various different sort of frequencies of light that we can actually choose to resonate in certain parts of the interferometer. So what we can do is we've got the main laser beam that goes in and does just as we've seen in the previous slides. But what we can do is actually modulate these laser lights, and we can put these sort of megahertz oscillations on top of these laser lights. And those megahertz oscillations kind of only probe certain areas of the detector. And so they only probe, for example, the corner part or the signal recycling cavity. And this lets us use some of this light to control exactly where the signal recycling mirror should be and exactly where the power recycling mirror should be, to essentially control the whole thing to femtometers. And then lastly, what happens is once all these signals come out, they get through to what's called the output mode cleaner, which kind of cleans all the beam up. There's a lot of junk and other weird stuff that comes out of the detector, light that doesn't contain any gravitational wave signals. So there's a final cavity right at the end called the output mode cleaner that strips all this junk light off, cleans it all up, so that all we have at the end in our output photodiode is this clean gravitational wave signal that we can just read out straight away. So before we just kind of look at the sensitivity bottom, we just kind of saw the total. Right? That's all the noises added up. But really what you have to sort of concern yourself with when you're actually designing and thinking about a detector and how we might improve it is what the contributions are at various different frequencies, because sort of some frequencies we're limited by some noises and other frequencies we're limited by completely different problems. And often or not, it's normally a trade-off, as always, that if you try and improve one noise, another one normally gets worse. So it's like this fine balance between all the various different noise sources to try and improve the detectors sort of in a broadband way. So generally speaking, there are the 2 types of noises that really limited us. There's things called sensing noise. So that's just noise that appears on that output photodiode that we saw before. Noise just kind of gets there. It's like photon shock noise and stuff, and it just kind of masks what a gravity. There's just a limit to how much we can sort of pick out a gravitational wave signal through that noise. So that's sensing noises. And then there are also kind of these actuation or force noises that really act on the test mass. So you can imagine if someone goes along and accidentally taps or shakes one of the test masses, that will look a little bit like a gravitational wave signal. And so there are a whole myriad of noises that can couple into those test masses. Those test masses have to be incredibly isolated from the rest of the world. So you have things like radiation pressure noise, the fact that the light that we're actually using to measure gravitational wave is actually just pushing, those photons are hitting that mirror and shaking it around. It's seismic motion, the fact that the Earth is just never motionless. There's always something moving around. There's wind, environmental noises, trucks driving past, people walking past, anything like that. All that can couple in and shake each test mass locally. Looks like a gravitational wave signal. There's also just thermal noises. The fact that there's just these objects are made up of numerous atoms, and they're all vibrating around individually, and each one of those is moving around a fair amount. And so that again looks like a potential sort of displacement inside the interferometer and can look like a gravitational wave signal. And then lastly, there are these control noises. So the fact that we have to control and try and put these mirrors in these precise femtometer sort of located positions, when we do that, we have just some intrinsic limit on how well we can actually control these things. And so that also adds a lot of noises. And so these kind of displacement noises, actuation type noises, all very much low frequency, as you can see here. Well, this brown one here is a seismic noise, there's thermal noises up here, like suspension thermal noises. There's other things like residual gas, which is just the fact that there's just a few sort of molecules bouncing around inside the arm still. It's a very good vacuum, but there's still a few things bouncing around. And every time the light kind of bounces and gets deflected off of that, it's a little bit of noise. There's other things like the thermal noise of the actual coatings that we apply. We use dielectric coatings on the mirrors to get these high reflectivity, very high reflection, low loss coatings on the mirror. They also have a sort of thermal sort of variability to them, and they also put a limit on them. And then this purple line here, which is kind of what we talked about before, it is this sort of quantum limit, which we'll talk about a little bit further on. But it's essentially just the limit of the fact that light is quantized, and that imposes some sort of uncertainty and noise limit on the detector. So a little about suspensions. Won't go too much into some of these things. Each one of these is obviously an hour-long lecture in itself. But the suspension systems are an incredible feat of engineering. If you ever get to visit any of the LIGO or Virgo sites, they're quite impressive structures to sort of look at. These things here, the big chambers in LIGO, is like 4 or 5 meters tall. They have these big blue sort of hydraulic isolation systems that bolt straight into the ground. And these things can sort of move these big vacuum tanks around on sort of the millimeter scale. And this kind of counteracts things like the tidal forces of the Earth. As the Earth goes around and the moon's like stretching and squashing things. You can actually get these tidal deformations that cause length fluctuations over 4 kilometers. These need to be sort of taken into account. That's done with these big like blue heavy piers. And then as you go along, we just end up having sort of a spring on top of a spring on top of another spring of isolation. And then eventually we have this big long sort of three meter long pendulum, which is suspended from. And so this whole thing is just making the ability to have basically like a super long pendulum. So we can get a very low resonance frequency. And so the idea is that we make this whole thing, these test masses down here. So here's the LIGO one, for example, look like a free mass. It's completely free in space. It's not being disturbed by the Earth that it has to be attached to. So LIGO kind of looks like this. Virgo is also a quite cool design. This is a big inverted pendulum. So actually this whole thing is just a big inverted pendulum, which sounds unstable, kind of is. But if you tune it exactly, you can tune it so that you can pick a very low resonant frequency for this whole device. And so you can get sort of incredible amounts of suppression and very low noise suppression. LIGO actually requires lots of active control to keep each one of these springs and sensors and systems kind of sort of aligned and working properly. Virgo, on the other hand, is very sort of a passive system. It's just kind of naturally there and naturally quiet and isolating. But both of them are essentially doing the same thing, creating a free mass, test mass, or essentially making it free for any kind of ground motion movements. And you can kind of see this here, and we can see this is the noise contribution just from the seismic sensors, from the seismic side. And you can see if you just look at the y-axis here, I mean, this gets down to ridiculous numbers of strain sensitivity quite quickly. And you can see by 100 hertz, this suspension stack, the seismic motion that's actually coming in is really only limited to like 10 to the minus 31 strain, which is incredibly tiny, way too tiny. We'd never get anything else down there at 100 hertz, but it is kind of limiting as we're at low frequencies. And so by having lots of these super long pendulums with multiple stages, lots of isolation systems, we actually get an incredibly sharp drop off of the seismic noise. And basically removing all this noise from the band that we're interested in, sort of 50 hertz plus. The interesting part here is there's also this extra peak here that pops up. It's called the bounce mode, which I quite like. It's the fact that as we actually make the detector too long, we actually have to end up as we go around the Earth, local gravity is actually pulling the test masses in sort of a different angle. They're both not coming down anymore. And so we actually, to make the detector work, we actually have to point the two mirrors at each other, even though they're kind of around the Earth. And so, of course, now we've got these tilted mirrors that kind of bounce up and down. And as the mirror bounces up and down, it actually creates a slight length variation, which looks like a gravitational wave signal because it's a small local displacement from the seismic noise. And so that actually looks, and so that gives us this big peak in the sensitivity. And so this actually gets a lot worse as you go to longer detectors, which might be a problem for things like for some of the detectors we want to build in the future. So then there's these thermal noises as well. Just give it a sort of sense of what the thermal aspects are. This is really just the sort of vibrations in all them. Each part of that mechanical system, suspension system, has got some thermal fluctuation in there. Those things will vibrate around, and that will eventually shape the test mass. The main limiting factor is actually the final sort of four sort of fused silica glass fibers that are used to hold the final test mass to the rest of the suspension. These things are incredibly high quality and under a lot of stress on the glass. This gives these things very high Q factors, so very narrow line width. So we condense a lot of this sort of thermal noise. We have a lot of gain at very particular frequencies here, which we call violin modes. We have a very narrow range of them, so we kind of limit how much of a nuisance they are. Problem is, these things are incredibly high Q. So if you actually knock around the detector a little bit, these things start ringing up, and they can take days to settle down if you're not careful and you don't have an active damping system. And if these things are actually shaking too much, they actually just limit you, and you can't actually operate the detector. And this has actually been one of the things we've been fighting against at LIGO recently over the last few months. For example, I was there commissioning back in November last year, trying to fix some of the system, and these violin modes were a particular pain. Every time we lost lock of the detector, these things would ring up, and you would no longer be able to use the machine for a couple of hours whilst you actually have to wait to try and settle these things down. And so they can waste a lot of time. But they also end up limiting and providing this sort of thermal noise limit, quite low limit, so it's not so bad, but again, at low frequencies, it's more of an issue. So squeezing is a complicated topic. I just want to mention it a little bit because you probably hear about it when people talk about LIGO. LIGO is kind of the first kind of measurement sort of device that was really used to squeeze light, or this sort of weird quantum state of light, to improve its performance. And essentially what's happening is that there's this ground state in the electromagnetic field. Electromagnetic field has got these two quadratures. It's got an amplitude and a phase, which is a sine wave. And there's a Heisenberg uncertainty that limits how well you can know the amplitude and the phase of a particular wave. And so this kind of fundamental noise exists everywhere. And anywhere in the detector that we have some kind of loss, or what we call an open port, which is a port which kind of leads off to nowhere, there's the ability of some of this kind of noise to try and get into the detector. And so the biggest problem is this noise that comes in through the dark port. It's very dark, and this vacuum noise kind of comes back in through the differential side of things, and it actually gets into the arm cavities. And by itself, the vacuum noise is like a photon or something. There's not much noise, but what happens is if you've got a megawatt of optical power inside the arm, and you get this extra photon coming in, that photon can beat with this megawatt of power and actually create radiation pressure fluctuations. And so this is why you see a lot of these noises all increase as we go to lower frequencies, because this is the fact that we have these free test masses, and they're easier to sort of shake at lower frequencies. And so as this vacuum noise gets in, beats with the high arm power, and actually shapes the test masses, and it looks like a gravitational wave signal. And so that limits us how far we can get there. And of course, the more optical power that we use, the bigger this radiation pressure effect is. So we kind of have this annoying trade-off again, as always, that we can increase the high frequency part here, which is actually due to shot noise. It's just photon count statistics, but then we end up making radiation pressure worse. We've got more photons, more radiation pressure. So squeeze light is this funny kind of quantum state of light that we can make. If we plot this on this plot down here, if we look at the two sort of different quadratures, amplitude and phase of this uncertainty of a particular optical field, this is like a complex phasor diagram, and you can see these red dots here is just a standard wave. A standard wave has got just as much uncertainty in the phase as it does the amplitude. We just got this in time. It kind of looks like a sine wave with some Gaussian fuzz over it, whatever. And so what squeeze state is, and where the name comes from, is if you pass this light or pass this vacuum actually through a non-linear system, you can actually shape this noise. And so this is why it's called squeezed, because you take this ellipse and you just squash it. And so what you can do is you can actually pick certain types of squeezed light, which here, for example, is amplitude squeezing. So you can see actually the noise is actually where the peak is high, is a lot lower. So you've actually got a lot less sort of amplitude fluctuation. We have more certainty of where the photons are, the number of photons that we've got. And so that can actually reduce the radiation pressure noise. So if you use this type of squeeze light, you can actually bring the noise in this band down a bit. There's the other sort of quadrature, the other stage is phase squeezing, which is actually what we use. And so this allows us to more accurately pinpoint the phase of the phase crossings around this sinusoidal waves. It's much noisier at the amplitude peak. And so this actually allows us to reduce the high frequency noise. And so squeezing is great because it's like increasing the effective number of photons that we have. It's reducing the amount of shock noise that we have, or the radiation pressure noise. And so it's the equivalent of being able to put more power inside the detector without having to deal with all the complexities of actually putting more power in the detector, like thermal issues and having a bigger laser or whatever, or control issues typically. And so there's that aspect, but there's also the fact that each time that we have a loss, this is the vacuum port. Everywhere that there's a loss, everywhere that there's a scatter, every time there's an absorption somewhere, a little bit of vacuum noise leaks back into the system. And so although the bulk of this noise actually comes from the dark port, there are various other sort of losses inside the interferometer. Every time we have an imperfect optic, there's kind of a limit that gets imposed. And this kind of shows here the total vacuum noise and then a breakdown of all the other various noises sort of contribute to it. So squeezing is a very cool sort of technique. LIGO has been using it now for some years. They're actually installing an A+, which is the upgrades going on at the moment. There's a new technique called a filter cavity, which actually allows you to rotate the squeeze state from blue to red between low frequencies and high frequencies. So before I said if you make one better, you make the other one worse. This cool technique, we're using a filter cavity. If you rotate the squeeze state in frequency, you can actually decrease the noise in both areas as well. So you actually end up getting this broadband improvement, both at low and high frequencies. And so this is already offering incredible benefits and is helping us well on our way towards the A+ goals for the fourth observation run, which should be starting in probably about 2 months. So of course, what we looked at there are mostly just kind of just theoretical noise curves. In reality, we have to do this thing and make this noise budget in real life as well. If any of you are particularly interested and can get access, there's the if you go to the git.ligo.org, there's the noise budget and the advanced LIGO noise budgeting tool, which is actually where this plot comes from. So you should actually just be able to get there and just grab it, and you should be able to make these plots, and you can plot different things and play around with it. It's quite fun to try out. But what this shows is actual real measured data from the third observation run about where we think all these various noises are. And so you can see that we've got things like thermal, seismic, gas noise, all these lines. These are theoretical predictions of where those exist. But there's a myriad of other noises, technical noises that we call them, that come in that limit the detector varying all across the band. So you see at low frequencies here, you see all these dot things. These are all the control noises I was talking about before. The fact that we have to make sure all these mirrors are pointing in the right direction and they're all femtometer position correct. By doing that, we inject loads of noise at low frequencies, which is actually one of the biggest challenges that we have to deal with for LIGO, is how we actually reduce this, because these are actually orders of magnitude worse than we expected them to be when we designed advanced LIGO. And so you can see down here, sort of the 20 hertz and less, we're really limited just by angular control. The fact that we can't keep the alignment of the mirrors sort of quiet enough that it isn't injecting too much extra noise that looks like a gravitational wave signal. Broadly, at high frequencies is not as bad. We're mostly still just shock noise limited. But over here, we can see down here, there's some other laser noise and laser frequencies and other photo detector noise, electronic noises. They're all just kind of hidden below the surface. So as the more you improve, the more you just keep running into new weird noise sources. And then each time you run into a new one, you have to be smart and figure out how to fix it. And then you just move on to the next one and just keep increasing power. And so the idea, the whole point of going to the sites and actually sort of commissioning and getting this detector working is really just kind of pushing this sensitivity down further and further, sort of little steps at a time. So that's kind of the way the LIGO is at the moment. I thought I'd also mention a little bit about what the future holds. And what's going forward. So for example, up here we've got another strain sensitivity plot, but we've got more sort of the future detectors we planned. A LIGO for the O3, this is the third observation run, the one that just ended just before COVID kicked off in April 2020. This is where we're at with the grey curve. This blue curve is where we like to try and be with advanced LIGO with the A+ upgrades. And so this should happen hopefully before the 2030s. We'll be getting around to this blue curve. Now, the other curves are sort of these upgrades. These are all kind of sort of ideas at the moment. None of these have been funded. None of these are definite, but these are all what we would do. Like, we know gravitational waves exist. We know these schemes and these interferometers can detect these things. How far can we push this design? How far can we go? And so the two big ones, the two big detectors, these are going to be much larger. We'll talk a little bit more, some pictures in a minute. The Cosmic Explorer and the Einstein Telescope. Cosmic Explorer is an American-led project. The Einstein Telescope is a European-based project. Voyager is what we think is the best possible detector you could build within the 4 kilometer sort of vacuum envelope infrastructure that exists at LIGO. So, I mean, if you could do as best as you could with the 4 kilometers, orange is about as good as you can get. We just struggle to get more than that. So that's about how much extra improvement we can expect if we spend a lot of extra money on the LIGO detectors. This yellow one here is actually an Australian idea. It's called is what's called NEMO. This is a high frequency detector. You can see that we kind of sacrifice lots of low frequency performance and really focused on the high frequencies. This is kind of an interesting idea I quite like. It's a bit like optical telescopes. You have different telescopes that are better at certain wavelengths and frequencies. And really, maybe we should be considering doing that for things like gravitational wave detectors. I mean, you think, oh, you can make a detector that's designed for constantly doing these trade-offs. Maybe we can just sort of ignore the low frequency and actually really concentrate on the high frequency and get much better sort of signal there. And so the high frequency is very good for things like neutron star, sort of inspire, the merger phases and all the rest of it, and really picking out sort of neutron star equations of state, stuff like this. And so that's really where that detector is focused. Whether you could build a smaller, cheaper detector that really focused on high frequencies and try and get that, just really focus on that one particular type of source. And so if you look at the redshift, I mean, the real winners in this redshift, like how far back you can see. You can also see on this sort of circular plot over here, the sort of azimuthal part doesn't really mean much, but it's more along the radial axis here. Here we have sort of the range of the different interferometers, same colors matching up for things like O3 and the distribution of where we think black holes are and neutron stars are throughout the universe. So how many do you think we're actually seeing? So here's GW 150914, from one of the first ones it detected, one of the big ones. And you can see that O3 is really just kind of probing just the beginning of this population of black holes. If we really start getting to A+, we kind of get halfway through, but it's not until we get to Voyager and some crazy things like ET and Cosmic Explorer where we're kind of really observing most of these throughout the universe, back to like huge redshifts. The same again for neutron stars. Once we end up getting to things like Cosmic Explorer and ET, we're really sort of probing, hopefully, as far as we know, a vast bulk of the sort of binary coalescences that we'd expect throughout the universe, which is pretty cool. So Cosmic Explorer, big American detector. As with many things American, it's just make everything bigger and better. So you times everything in LIGO by 10, and you essentially don't get that far off of what the Cosmic Explorer design is. So we know advanced LIGO works. We just need to make it bigger. So there's only so much power that we think we can get in the detector. That's still kind of an open question. So there's like an extra factor of 2 power. But the big thing is we actually make the detector much longer. We actually make that 40 kilometers long instead of 4 kilometers long. And so many of the noise sources scale very favorably with that, as I'll tell you in a second. But if we just look at the noise sensitivity budget, we can see how much more we win just by making everything much longer, bigger, heavier test masses, so they're less sort of susceptible to things like radiation, pressure noise. And so you can see that we've really squished all this low frequency noise down. And so we're getting this great sort of sensitivity down to 10 to the minus 24, about 10 hertz. And then we dip down into this really big bucket that's nice and wide. And we're really only limited here by quantum noise of light. So we can improve this by trying to get more power in there. Once you've built that instrument, you can always try and get more power into the thing. Bigger lasers, better cavities, less losses, stuff like this. These are just kind of incremental things that we try and improve on a technological sort of timescale of like decades and stuff. But you can also then try and use more and more squeezing. So the more squeeze light you can do, you can also kind of keep pushing this quantum noise down further and further. And so you can get this great sort of deep, large bucket. Obviously, the problem with this thing is it's 40 kilometers long. You start running out of Earth quite quickly once you get to these sort of lengths. And at this point, you actually really start having to, if you imagine sort of the curvature of the Earth, you really have to start digging straight through and then putting these tests, the sort of the stations, right, and burying them down into the ground. Otherwise, the curvature of the Earth means these things would be like 20, 30 meters off the ground if you just try to balance it in the middle, which is no good because it'd just be flopping around in the wind and would be too noisy. If you look at just how these sort of noises scale, a lot of the noises kind of scale. Some of them scale linearly with a length, other ones scale more favorably with like length squared. So you can quickly start taking some of these very problematic noise sources, things like coding Brownian and substrate thermorefractive noises. These are very difficult material problems to solve. Trying to make the most pure, low loss, low noise codings that go on the optics that we use. A very expensive problem to fix as well. You can fix a lot of this by just making the thing really long. And the idea is that the longer you make it, the more beams diffract, the bigger spots you have on the test mass, the more you average, the bigger your spot is on the sort of optic, the more you average over all the atoms vibrating around, and so you win. You win considerably by making the spots larger, interferometer longer, essentially. But pretty much all the other ones also scale very favorably as well. So we can get rid of a lot of stuff other than sort of quantum noise and such, which also, as we see on the last plot, is still kind of a limit, but you can get rid of a lot, which is very useful. So this is a nice idea because it's basically taking technology that we know how to do today, in theory, just need to make it bigger and slightly better. But these sort of things, we're kind of hoping these detectors are really kind of on the late 2030s, 2040s timescales of becoming operational anyway. So by then we'd already have LIGO probably improving things by several factors anyway, or demonstrating how far we can probably get. Nice thing about Cosmic Explorer as well, there might be some options here about some sort of teaming up with the Americans to maybe get what we'll call Cosmic Explorer South, Cosmic Explorer Australia. Australia was obviously very big, flat and empty in a lot of places. So if you wanted to find 40 kilometers of empty space to put something, Australia is a pretty good spot, especially since now quietly sort of seismically sort of inactive the places, and quite a lot of empty spare land going around places. So potentially there might be the case of maybe one of the Cosmic Explorers in America, one's in Australia, maybe two will be in Americas, who knows. There's sort of ideas of kind of exploring as a community about what's the best way to go forward there. The other cool project, the other one I work on is the Einstein telescope. So this is a European-led project. And this takes a slightly different approach. It's more along the approach of we end up having multiple different interferometers that are kind of tuned for certain different frequency bands. Here's a beautiful render of this whole thing. It has to be underground. There's not a lot of space in Europe. It's very dense. There's lots of people everywhere. So it's very hard to find the amount of space that you'd need. And so the Einstein telescope will all be underground, 100 odd meters underground or whatever, in these massive monumental cavernous spaces. And the idea is instead of being at right angles like you imagine LIGO to be, they're actually at slightly less, so like 60 degrees. And the idea is you have these three big underground caverns, and then we have multiple interferometers all kind of pointing towards each other. And so you get this redundancy effect. You also have multiple interferometers all at the same location, so you get better sort of antenna patterns, seeing detectors coming, signals coming from all over the sky. But there's also we have these what are called the high and the low frequency, which is actually what the low frequency, these blue towers here, it's color coded so you can see them, and the red one is this high frequency one, so it's more sensitive to the higher spectrums. And so these things, you can probably see these small tiny pixels down here. This is a cavernous monster. These things will be huge. These pixels down here are people. So this will be an incredibly large. This is big science stuff that will happen. And the Einstein project, the Einstein telescope project, is actually well on its way to try and sort of formalize itself and actually sort of try to start bidding for some of this money to start this project. So there's two kind of locations. No one's decided where it's going to be yet, unsure. One of them is in this sort of tri-country area where Amsterdam, Belgium, and Germany kind of meet near Maastricht. And the idea would be that you could put one corner station in each country, and so you can bring three countries together. So it's got a lot of benefit of like bringing in multiple countries to fund it, run it. Sort of people take more pride in running these types of big projects and getting involved. There's, as I said before, there's this low frequency and high frequency. It starts really becoming a problem. I mean, if you're really starting to put megawatts of power to improve your high frequency sensitivity, but that makes controlling the thing very, very difficult, so that you end up injecting all this extra noise at low frequencies, so you ruin it. At some point, you might think, well, why don't we just build two different types of detectors? We build one that's meant to just be low power for low frequencies, much easier to control, much quieter, lots less problems, radiation pressure instabilities and things like this. And then we just have these extra ones. And so that's the idea behind this triangle pattern, is that we actually end up fitting in multiple interferometers down the tube. So there actually be there's three of each. So in each kind of corner would be the corner of maybe three high frequency detectors, and then there'd also be three low frequency detectors as well. So this provides a lot of redundancy. As one of these detectors is off, we could be working and fixing and improving the other one. If one of them just decides it doesn't want to work today, then there's always other ones that are online. So we should have this fantastic uptime, so that we're just constantly observing nearly all the time. This thing will only be about 10 kilometers. It won't be 40. There are actually some significant challenges of actually making something run at 40 kilometers. So something between 10 kilometers is probably a good trade-off, maybe up to 15. You also have a lot more detectors that you can kind of average the sort of add the signal up. So you can, with 6 detectors, you can actually start adding the sensitivity up. So you can actually end up getting, even though it's shorter, you can still actually end up getting quite a lot of extra signal there. And so the sensitivity here kind of looks kind of weird. It's got a few extra lumps and bumps. The low frequency one is this part down here, low frequency. So this will really go down to sort of a few hertz sensitivity. And then the high frequency detector will really pick up more above the 20-30 hertz. And so if we overlap these, depending on how you want to design the detectors and how you want to overlap them, you can try and get more sensitivity or less sensitivity in these various areas. But yeah, the idea here is really try and separate these out. And so you kind of lose a little bit here compared to what Cosmic Explorer does, which has a much more wider, smoother bucket. And obviously this is a lot more complicated. There's a lot more stuff that goes on. Low ET, low frequency, because as I was showing before, there's lots of thermal noises, suspension noises, all other complicated stuff. A lot of this stuff gets better if you go to cryogenic sort of interferometers, cool things down to 4, 5, 10 Kelvin or something. That obviously adds a lot of complexity, cost, and other issues that we're going to have to deal with. So ET low frequency is a very difficult machine to try and figure out how we're actually going to run it. ETHF, again, is something very similar to advanced Virgo, advanced LIGO. We probably know how to do that. That's quite a safe option. That's not too dissimilar, really, to advanced, to things like Cosmic Explorer or advanced LIGO, apart from the fact it needs about 3 megawatts of power in its arm cavities. And so just as before, as I said, there's 2 different suspension approaches. So for ET low frequency is kind of an interesting sort of thing to look at about what are the differences and what kind of route you might take. So 2 very different sort of design philosophies between the way that Virgo and LIGO does things. But if you look at this, the LIGO is very sensitive at the moment in our sensitive in the band of interest, sort of this 10 hertz plus area. But actually, when you start looking at much lower frequencies, for example, we have to make huge improvements, 7 million times better at 3 hertz compared to what LIGO is doing currently to make something like ET low frequency work. So to really reach these final goals, a 7 million times improvement is an incredibly difficult challenge to actually meet. But even then, if you already look at things like the Virgo suspension, this passive isolation system, that already gives you significant wins over what, for example, LIGO is doing. So although it seems like a big sort of cavern to try and get through at the end of it, trying to reduce all this noise, there are various different technological sort of decisions and ideas that we need to try out over the coming decades to really kind of sort of improve this. So from Virgo, it's only 250,000 times better, which is a lot better than 7 billion. Just a little bit more on the NEMO part. So we've actually been trying to figure out roughly where you might be able to put this. It's only 4 kilometers long. So if it was a small cryogenic detector, it needs to be cryogenic so that we can cool the optics down, because we actually need something like 5 megawatts of optical power inside the arm cavities to really get this high frequency sensitivity. We end up being limited a lot of times, but also not only by the quantum noise, but there's also problematic violin modes that also come about. And there are various places that we could put something like this in Australia. Lots of places obviously down south, out up in the middle of nowhere as well. And so there's plenty of areas where we could do this stuff. Obviously, we want to try and keep it somewhere that's close to sort of civilization, so that people actually want to come there and work there and live their lives and have families and stuff near the sites. So it's kind of focused mostly around sort of down the southeast area and out towards Perth area. But this is very much still an idea that everyone's exploring. None of these things are necessarily set in stone yet, but an interesting thing that we might be able to sort of construct and build over the coming decades. So this is all I kind of want to talk about today. Maybe you have some questions. One thing I'd like to point out, if you do kind of want to play around and make your own noise budgets for gravitational wave detectors, there's this fabulous package called PyGwink. It's the Python gravitational wave interferometer noise calculator tool. You can install it via pip. We just do pip install Gwink in spiral range. There's a load of notebooks and stuff that if you're interested in, I can also send around as well if you plan to use it. But you can get all the advanced LIGO, Cosmic Explorer, Einstein Telescope noise budgets, dig into these things and play around with them. So yeah, fully, there's a nice video as well, but also goes over some of the design decisions and how to use PipeWing to do some of this stuff. So yeah, if you have any more questions or anything, please do ask now, or yeah, if you have any more in the future, feel free to email me. Okay, thanks so much.
Thanks very much, Daniel. This was a very fascinating talk, I have to say. It's very interesting. Are there any questions? Yeah, Matt.
Hey, Dan, that's really, really great. Just so I can check my understanding, you show those noise curves with lots of spikes in it. So does that mean at the moment, LIGO sort of looks in the windows between the spikes? So there's nothing you can do about it?
Pretty much. Well, there's so the violin modes of these ones down here, they're like 500 hertz. So there's actually like, I think there's probably dozens of them around the five. So this is the first harmonic, and here's the second harmonic at kilohertz. So these violin modes, they're a nuisance, but you can suppress them. So what we actually do is you can see them ringing up, and as they're ringing up, you can actually apply very tiny forces to the test masses at just the right frequency and phase. You can actually kind of gently cool them down. And so after, if you look at some of the LIGO data, after very long locks, if it's been locked for like 5 or 6 hours, you'll actually see a lot of these peaks will disappear and be suppressed quite a lot. So you can actually get rid of them. They're just a nuisance, because every time you lose one, you run it again, they ring back up. So it's just kind of
I understand. So so what you're showing for next advanced A+, you showed quite a smooth curve, apart from that one sort of spike. That's also representative of what it's going to look like. We don't need to worry about violin modes then.
They'll still be there, but ideally we have. Sorry, I'm just trying to find the plot. Where's the one? I guess you mean this peak here, this kind of thermal.
Actually, it was maybe later on. I think it was shown again.
This one again, or
maybe a couple forward, I think it was. Yep, there it is. So that
this one.
Yep, that
this
dashed line there. Yeah. So that's pretty smooth. It's going to be smooth.
Yeah, we'd get. Yeah, you can get rid of them. Yeah, and even that peak there, you could probably get rid of eventually. I think it's mostly there just kind of highlight that those violin modes will be there at some level. Their natural kind of sort of thermal limit is really kind of at the level, unless you do something active to try and get rid of them.
Yeah, cool. Well, thanks very much.
Yeah, no worries.
Okay, so there is a question in the chat. How are the mirror positions adjusted so finely?
Yeah, so there's a range of different actuators that we can use. And so you can imagine we've got this big suspension chain. Obviously this big suspension is just kind of there hanging at the bottom, and it's kind of freely hanging. And so what you can do is you can actuate on some of these upper stages. And so you can just have like magnetic actuators that push and pull this optic, and it just shakes that pendulum. And then that force gets sort of taken down to the end test mass, and you can control things like the alignment and the tilt just by changing these upper stages. So we like doing that because those couple of pendulum stages also end up filtering out some of the control noise, because again they have this like 1 on f squared kind of reduction in the noise. That's quite nice. But also for controlling the actual what we call the differential arm mode. So this is we actually have to control the differential length changes in the arms to make sure they don't get too big. To do that, what we actually do is we use what's called the electrostatic actuator. So on the optics, I don't know if we can actually see that. No, you can't really see it, but on the back of these test masses, there's actually another optic which is called reaction mass behind this thing. And on each one of these, there's kind of this thin gold coating that's applied to it. And these are actually what we do is apply large, high voltages, like hundreds of volts, and this creates an electrostatic force. So from this reaction mass, we can apply a voltage, and that then kind of pushes this reaction mass and test mass apart from each other. And so that that electrostatic drive actually lets us control the test mass position to easily femtometers. There are also more advanced ideas. The problem with the electrostatic drive is you end up with all the test mass, because it's now sensitive to electrostatic fields, is now obviously sensitive to stray electric fields inside the chambers, so that can introduce more noise. So some people actually want to get rid of that actuator altogether and actually go to what we call the photon actuator, which is where we actually use lots of lasers, and you just shoot them at the test mass. So if you have like a another 30-40 watt laser, you can actually control and move the test mass just by radiation pressure, which is pretty cool. And if you have like a ring of them, you can control alignments and all sorts of stuff. So in the future, we'll probably move away from some of the more electronic drive problems, because we also have lots of problems with things like ground noise, extra, you plug something in wrong at one of the end stations, you end up getting your ground now becomes noisy, and that injects noise straight into your test mass. So we built this wonderful suspension system. We make the whole thing sensitive to electric fields, and then we actually just inject noise straight in at the bottom, which is very unfortunate. So yeah, we want to get rid of that.
Okay, so there was another question in the chat, and that is the noise generator only limited to the LIGO frequency range, I guess, F range? Frequency.
Yeah, I assume you mean PyGwink. So PyGwink is mostly designed for the ground-based detectors. There's nothing to say that it couldn't be used for other versions. It's mostly just that the noise calculations that are in there and included are normally kind of simplified into the regions that we're interested in. So they might not necessarily be true at like 10 megahertz or something. But within that sort of 0 to a couple of kilohertz region, they should be accurate. But there's nothing stopping you from, it's open source, so you can always go in and extend it to larger frequency ranges if you want.
Okay, next question. I'm assuming, so that's Amin. I'm assuming all the noise reduction techniques you talked about are presently implemented in LIGO. So are there any WIP techniques that are being experimented with?
Yeah, so there's still a lot of work to go in many regards. There's the squeezed light state, for example. At the moment, we talk about this in like decibels of noise reduction. So for future detectors, we're using squeezing, but we're kind of only really getting about 3 dB, 4 dB, which is roughly a factor of 2 improvement, roughly. But for some of these future detectors, Cosmic Explorer and ET, these really rely on things like 10, 12, 13, 14, 15 dBs of squeezing, which is an incredible amount of noise reduction. But the problem is the more squeezing that you use, the sort of narrower that ellipse gets, and the more sensitive it is to things like losses and sort of imperfections in the system. And so at the moment, whereas we can get things like 3 or 4 or 5 dB working okay, trying to push up really that much further really requires much finer control and better control of things like the shape of all the mirrors. Kind of alluded to in the talk, as we put more power in, all the optical cavities kind of deform and stretch and squash and then become weird shapes. And that kind of quickly degrades the amount of squeezed light that we can actually use and stuff like this. So there's a lot of improvements that need to be done on the sort of thermal compensation control of the shape of the optics. That is something that will be crucial for the future. We're actually building a new test facility here at Adelaide to actually really try some of that stuff. We're going to have a LIGO test mass, and we're going to make all sorts of new actuators to try and test those things. Another interesting aspect as well, I mentioned that one of the big problems is these low frequency noises. This again comes from the fact that we have to try and control the instrument too much. It's not quiet enough as it is. If we could really build these beautiful passive systems that isolate everything, it would be great. But the problem is each one of these suspensions, like we need dozens of them essentially, like everything has to be suspended. And so one of the big problems is the fact that each one of these suspensions are kind of isolated from each other. They're not kind of locked together. And so each one of these things move around separately. So one of the big improvements, one of the things I'll be excited to see in future versions of like advanced LIGO Plus and stuff, is actually where we start making extra interferometers that where we tie all these suspensions together. So what's called suspension point interferometry. So what we end up doing is locking all the suspensions together. And so that would actually require making more interferometers that connect all the suspensions together that isn't just LIGO to try and lock everything. So now the whole of LIGO, essentially suspensions would all move rather than each one kind of moving separately, which introduces more noise. Everything would move in tandem, which would mean our control system has to do a lot less. And so less actuation, less force needed, less noise. And then the next big one is coating thermal noise. That's the big material problem. We still don't have the coatings fully done for advanced LIGO Plus at the moment. We're kind of getting close and moving in that direction, but it's incredibly difficult and time consuming trying to find the right sort of chemical coating requirements and sort of recipe essentially for making something that's low noise enough. So yeah, that's a big work in progress.
Okay, last questions. I'm not so concerned about the time limit, so that's because we don't have to watch the time for catering, but that's the last question, I would guess. How can an inverse pendulum be controlled so finely? Because I guess the inverse pendulum is unstable by design, isn't it?
It is, yes. And so there's lots of extra actuators that you have to tie around it to try and make it. So it's not a purely inverted pendulum. It's kind of a combination of an inverted pendulum and a normal pendulum. And you're basically, what you're trying to do is cancel these two things out. So you've got two optical springs. One's kind of got a negative and a positive coefficient. And so you kind of you're pushing one up, so you're trying to cancel each other out, so you're just left over with just enough positive, sort of negative spring, sorry, so that you end up with something that's actually stable. And so it's just kind of a fine balance. There's extra bending and actuators and various other parts that kind of interact there. But those interactive parts or active parts are a lot less than what, for example, LIGO requires or needs. So they benefit, I think, there from some of the noise and suppression of it.
All right, there is one other question, but I think we should come to an end, and you can look at the question, maybe then answer it in the break after the next talk. So with this, I'll thank you again, Daniel, and I think it was a very interesting talk.
Yeah, no problem. Yeah, thanks for having
me. All right, so the next speaker is Ilya Mendel. He's so he is around. Very good. While you set up, Ilya, I'll just say a couple of words. So Ilya is he did his PhD in physics at Caltech, and he's interested in theoretical astrophysics. And after his PhD, he went as a postdoc to Northwestern University and to the MIT. And after that, went on to Birmingham, which is obviously in the UK, where he, after a while, got promoted to professor. And he since then has moved to Monash as a professor of theoretical astrophysics. Ilya is interested in all kinds of sources for gravitational waves. And so he will be talking about the other end of the gravitational waves. We've heard Daniel talk about the detection. Now Ilya will talk about the origin of the gravitational waves. And today he's talking about EMRIs, that's the extreme mass ratio in spirals. And that's quite interesting types of sources, both from a theoretical point of view and from the observational point of view. And so with this, I'll hand over to you, Ilya, and wait your talk.
Thank you very much, Jörg, for the very kind introduction. So I had hoped to give this talk in person as a whiteboard talk, because I really think that the subject lends itself best to that kind of discussion. In the absence of being able to do it in person, I'm going to try to still give a whiteboard talk, so rather than PowerPoint slides. So we'll see how that's going to work out. I apologize if it doesn't work too well, but I really think it will be more fun this way. And I should also say that I would actually encourage people to please interrupt me. You don't have to wait until the end. I am very happy to hear questions at any point. And there is no particular set of material that I'm trying to get through. So if we have more discussion, I'll just be much happier. And you might actually be able to stay awake. Okay, so let's just very quickly start. I'm going to try a different color because black holes have to be black, of course. So the situation we're considering is the following. We have a massive black hole. Let's say, as we'll see in a moment, we're thinking of something like the kind of black hole that's sitting in the center of our galaxy, Sagittarius A star. So this may be hundreds of thousands, maybe millions of solar masses. We'll use big M to denote the mass of this large black hole. And we have an object that's going to be scattered towards this black hole and eventually will be captured and will spiral into the black hole gradually. I'm not very good at drawing this gradual spiral in, but it's actually a much more gradual spiral in, as again we'll discuss in a moment, than, for example, compact object binaries that LIGO is observing, which are moving in far more rapidly than these extreme mass ratio in spirals. And So this compact object has a mass little m, where little m is much smaller than big M, hence the term extreme mass ratio in spiral. Now, how much smaller? Well, little m may typically be a stellar mass black hole, say 10 solar masses, or a neutron star, say 1.4 solar masses. It could even be a white dwarf of point few solar masses, although in general, white dwarfs, well, yes, let's just stop there for a moment and say that yes, it could also be a white dwarf as well as a neutron star or a black hole. Now, what are the typical masses big M that are relevant to us? Oh, by the way, I should say the reason it cannot be a normal star, of course, normal stars also get sucked into massive black holes, but normal stars get tidally disrupted. They get shredded by the gravity of the massive black hole. Actually, maybe we should do a little derivation. After all, it's a whiteboard session to understand why they get shredded by the gravity of the black hole. So the thing you should consider when considering a star, so suppose this little m is now a star with some physical radius little r, rather than a black hole, could be a white dwarf as well. Suppose this is some distance big R from the black hole. Consider the tidal gravity operating on this across this star. By the tidal gravity, I mean the difference between the force on the black hole on the, let's say, the left side of the star and the center of the star. Okay, so the tidal gravitational force tidal is, I'm not going to be particularly careful here with my notation, and certainly factors of 2 will drop, but it's going to be something like FGM. Actually, maybe I should look at tidal acceleration. So let's, when I say tidal force, I really mean tidal force per unit mass, specific tidal force or acceleration. So it's FGM over big R squared minus F minus GM, forgive me, over, let's consider the far part of the star the way that I've written it down because I want this force to be positive. So R little r plus big R quantity squared. Now, of course, this, as you can very easily see by doing a first order Taylor expansion, and the quantity little r over big R is just order of magnitude. Again, I'm ignoring factors of 2, GM over big R cubed times little r. Compare this to the self-gravity, the gravitational acceleration on the surface of the star from its own self-gravity. That is equal to G little m over little r squared. And so setting these two things equal to each other, which is the point at which the star gets tidally disrupted, which material from the surface of the star is getting ripped off by tidal forces, which are now overcoming the self-gravity of the star. If you set these two things equal to each other, you find that the criteria for tidal disruption is that big M over little m is big R over little r cubed, or another way of writing the same thing is that the radius of tidal disruption is the stellar radius times the cube root of big M over little m. So now consider, for example, what would happen if big M was a 1,000,000 solar mass black hole, little m was the sun. So that means that its mass is 1 solar mass, its radius is 1 solar radius. Then this would be about 100 solar radii. Now, why is this important? Well, 100 solar radii, okay, a solar radius is about 7 times 10 to the 5 kilometers. Oh, sorry, there was a quiz that came up, apologies. Okay, so a solar radius is about 7 times 10 to the 5 kilometers. So this is about 7 times 10 to the 7 kilometers. That means the sun, if it gets any closer than 7 times 10 to the 7 kilometers to a massive black hole, will be tidally disrupted. For comparison, consider the ISCO radius, the innermost stable circular orbit radius of a Schwarzschild black hole with a mass of 1 million solar masses. So radius of the ISCO is 6 GM over C squared. GM over C squared is a really useful thing to know. That's how you convert mass into units of distance. And the important thing to remember is, and very frequently I won't even bother writing big G and little c, because of course, most of the time as relativists we work in units where big G equals C equals 1. But in the end, we find conversions useful. And so just the thing to remember is that a solar mass, you might think is 2 times 10 to the 33 grams, but that's silly because that's a very large number and it's very difficult to work with. And as relativists, we find it much more convenient to say the solar mass is either 1.5 kilometers or 5 microseconds, 5 times 10 to the minus 6 seconds. So if you remember the solar mass is 1.5 kilometers or 5 microseconds, it turns out you can do all sorts of physics very easily. In this particular case, of course, it's, okay, we multiply by 6, so it becomes 9 kilometers, let's say 10 for round count, because we're also doing order of magnitude calculations. And then we have to multiply by 1 million, because of course we're talking about 1 million solar masses, not 1. But so that means that our ISCO in this case is going to be something like 10 to the 7 kilometers. So, but remember, we just said that the sun is getting tidally disrupted at 7 times 10 to the 7 kilometers, which is larger than the innermost stable circular orbit radius. So what that's telling you is that, in fact, the sun can never get to the innermost stable circular orbit. A normal star can never get to the innermost stable circular orbit. It's going to be tidally disrupted well before it gets there. And that's basically a way of saying that we're not really going to see these extreme mass ratio in spirals from normal main sequence stars. We can only see them from white dwarfs, neutron stars, or black holes. Questions so far? Okay. What about the typical mass of the black hole that's most relevant? Well, to figure out the typical mass, what we really should think about is what is the frequency of gravitational waves coming from the innermost stable circular orbit? Well, okay, we know in general how to compute a frequency. A frequency is given by 1 over 2 pi if you want to be careful, times root gm over r cubed. That's the frequency of a circular Keplerian orbit. Now, okay, you might say, wait, hold on, this is all classical. We're surely relativistic. Within small corrections, as long as we're outside the ISCO, this is fine. Of course, the gravitational wave frequency is twice the orbital frequency. So that means we need to cross out this factor of 2. And if for r, we put in r ISCO, which is this quantity here, you immediately see that everything becomes just a constant. There are some g's and there are some c's. The only thing that gets interesting is that the r ISCO is proportional to mass. So I have mass cubed in the denominator here. Mass over mass cubed gives me 1 over mass. So clearly the gravitational frequency scales is 1 over the mass. I'll save you some arithmetic and just write down that this is equal to 4.3 kilohertz divided by the mass in units of solar masses. So now, if you ask yourself, okay, where do you want the gravitational wave frequency to fall? This is the gravitational frequency at the ISCO again. If you want this to be in the sweet spot of your detector, which you probably do, that tells you something about the masses of these central black holes you're interested in for extreme mass ratio in spirals. So I don't remember anymore exactly what the peak frequency of LISA in its current forecast is, because when I started in this field about 20 years ago, I should say, LISA was supposedly only 10 years away. I think now it's a little more than 10 years away, so it's actually receding back in time, which is a remarkable thing to do over 20 years. But obviously the exact spectra have changed quite a bit in those 20 years, which leads me to think that they're quite plausibly going to change again before the instrument is launched. So I wouldn't worry too much about the exact value, but let's say it's a few millihertz, maybe up to 10 millihertz is the bucket. So if I set this to be about 10 millihertz, this actually tells me, of course, what the mass should be. And this tells me that the ideal mass to get this thing to be about 10 millihertz should be about, oh, maybe 500,000 solar masses. Maybe if we say that it's not 10 millihertz, but 5 millihertz, we would get about 1 million solar masses. So something in this ballpark, in fact, is the right frequency, the right mass scale for the massive black hole. Of course, it doesn't mean that you cannot have more massive black holes or less massive black holes. It's just going to be the case that if your mass is different, then generally speaking, you will your most of the energy output in the gravitational waves, which of course is happening late on as your object is spiraling into the innermost circular orbit, will be in the wrong frequency range. Now, of course, the ISCO is going to be closer for more rapidly spinning black holes. For a maximally spinning black hole in the prograde orbit, the 6 gets replaced by 1. So that means that the ISCO frequency gets higher for prograde orbits into rapidly spinning black holes while keeping the mass the same. And that means that actually you are really potentially thinking about higher mass objects if the black holes are going to be rapidly spinning. So if the black hole is rapidly spinning, then maybe you don't have to have just a 500,000 solar mass black hole. You can have a few million solar mass black hole if it's sufficiently rapidly spinning. I'm going to pause again for a moment and see if there are any questions. Please do feel free to interrupt. Okay, I don't see anything in the chat, but also just feel free to speak up because I might not see stuff in the chat. I'm going to see if I can momentarily save this. Okay, and let me try to erase this and start from scratch. Actually, maybe let me see, is there a way to scroll it? Not that I know of. Okay, actually, let me close this and then restart it.
I could have just cleared it for you, but that's fine.
Oh, okay, sorry. All right, it's all right. Okay, oh, there's a way to clear it? Yes, I see it now. Okay, thank you. Sorry, I lost my pen. Okay, good. All right. Thanks a lot for that. Again, sorry for the distraction. Okay, so now, okay, we know that we're talking about roughly 1 million solar mass black holes. That's already useful because the next thing we want to do is ask ourselves, how often do these extreme mass ratio in spirals happen? Now, there's been a lot of work on trying to do calculation of extreme mass ratio in spirals, involving a lot of very interesting physics about galactic center dynamics and lots of assumptions. I'll try to highlight some of the assumptions in a moment and some of the uncertainties in those assumptions, but suffice it to say, there are a lot of uncertainties. And so I am very far from being convinced that we actually have the tools to make very accurate estimates. We have the tools to make very precise estimates, and there are plenty of papers in the literature that have made very precise estimates of merger rates and event rates, and people say things like, well, if you have this sensitivity for LISA, you expect to see 37.2 IMRIs in its duration, but if you have this other noise curve, you might get 42.5 IMRIs. Okay, it's 42.5 plus minus an order of magnitude. So let's try to think about the order of magnitude part and not worry too much about the fine details for now. And we'll highlight some of the interesting physics, but it's going to be, I think, rather the other way around. Once Lisa starts detecting MRIs, then we'll have a better constraint on some of those physics. Unfortunately, it's not clear that some of the questions are things that we really cannot address without Lisa, which is actually what makes Lisa so exciting. So I'll give you a very simple calculation, and this is a firm upper limit on the rate of MRIs. So this one, I can absolutely stand by and tell you that the rate of MRIs cannot be any higher than this number. Could be lower, could be zero, probably not zero, but could be much lower, but definitely cannot be higher. Here's the way to do it. Suppose I have my, again, for simplicity, 10 to the 6 solar mass black hole. Suppose again that my typical object that's spiraling in is a 10 solar mass object. Now I have a question. Over the age of the universe, how many 10 solar mass black holes could this 10 to the 6 solar mass black hole swallow in order for its mass to still be in the 10 to the 6 solar mass range? Okay, everybody's being very shy. That's okay. Oh, please.
Is it 100% efficiency? If that's fine. At least.
I'm going with 10 to the 4.
10 to the 5, right?
Yeah.
Yeah. So it's a million solar mass central object. It can swallow, we're being very optimistic here. It can swallow 10 solar mass objects, right? Well, okay, if it swallows more than 100,000 of them, then its mass rises by an extra million solar masses. So I'd say that means it's not really a 10 to the 6 solar mass black hole anymore. It's a 2 times 10 to the 6 solar mass black hole. So order of magnitude, it can have the number of MRIs per black hole over the age of the universe is 10 to the 5. Now, how old is the universe? Well, 14 gigayears or so. Again, with our precision, 10 gigayears or 10 to the 10 years. So that means the rate per black hole, per massive black hole, is 10 to the 5 divided by 10 to the 10 years. That's 10 to the minus 5 per year. Okay, the next thing we want to know is how common are these massive black holes? Well, it seems like every galaxy has one, but of course, one of the questions is, what's the distribution of black hole masses in galaxies? Because not all galaxies have million solar mass black holes. Some galaxies have lower mass black holes. Many galaxies have higher mass black holes. And that's actually not so easy because 10 to the 6 solar masses is about the bottom range of where we can comfortably measure black hole masses. The way that you normally go about measuring a black hole mass, it's very hard to actually measure it exactly. In the case of our own galaxy, there is a fairly exact way of measuring it because we can actually see S stars orbiting around the massive black hole, and we can resolve their orbits. And this is what Gez and Gensel got shared a Nobel Prize for recently, their observations of Sagittarius A star. And so you can actually just look at astrometrically at the properties of the orbit. You get the period, you get the physical orbital size, if you know the distance to the galactic center, and that tells you that the mass is about 4 million solar masses. But that's not easy to do in other galaxies. And so usually you're relying on some indirect metrics, some correlations with things like the velocity dispersion in the galactic center, with things like other properties of the galaxy. So there's a correlation between the black hole mass and the mass of the bulge, the sort of the entire mass of the galactic center. Those things are typically well correlated at higher masses and also easier to see, frankly, at higher masses. It's kind of hard to resolve the inner details of low mass galaxies far away, given that, of course, low mass galaxies are the ones that will typically host lower mass black holes. So we don't actually know that much about the, we don't have as good a measurement of the things that are in the million solar mass range as we do in the, say, 10 million to 100 million solar mass range. But roughly speaking, okay, a galaxy like ours in Milky Way, there's roughly 1 per 100 cubic megaparsecs. So, some estimates suggest that maybe things in this mass range, 10 to the 5.5, 10 to the 6 solar masses, you're looking at maybe a space density of maybe 1 per 1,000 megaparsecs. So in other 1 per 1,000 cubic megaparsecs, I misspoke. So you're looking at 10 to the minus 3 per cubic megaparsec. Maybe it's a little bit higher. Maybe it's 10 to the minus 2 per cubic megaparsec. But let's for now write down 10 to the minus 3 just for round count, especially given that we are overestimating things elsewhere. I'm not too worried if we slightly underestimate things here. So if I now take a product of these two, so this is the space density of galaxies with the relevant, not all galaxies, but galaxies in the relevant mass range, and I multiply this by the maximum merger rate per such galaxy, I multiply these two quantities, and I end up with a overall rate of EMRIs, volumetric rate of EMRIs of 10 to the minus 8 per megaparsec cubed per year. Or if you prefer, if you don't want such small numbers, here's a big number, 10. It's just going to be per gigaparsec cubed per year. Now, that's actually a pretty big number. It's in fact getting close to the kinds of rates that LIGO is observing for stellar mass black hole mergers. Do I really believe that EMRIs are that common? No. This number is almost certainly overestimated by a couple of orders of magnitude. There are multiple reasons for that. First of all, black holes actually mostly grow by gas accretion. So only a tiny fraction of this, or a small fraction of this total mass that you see is actually coming from extreme mass ratio in spirals. There are some direct captures, meaning you just have a direct plunge in, you don't actually see much of an extreme mass ratio in spiral. So that's not going to, that may add some mass, and it's technically a complex object falling in, but it's not going to be something detectable as an EMRI. There are also some of the mass growth comes from tidal disruptions of stars. We know that actually these relatively low mass black holes, it seems, do frequently gobble up stars as well. And of course, that means that some of their mass growth is also coming just from gobbling up gas and stars. So that means that at least some of the mass growth is coming from that. And of course, in that case, if the disruption is happening too early, you don't get an extreme mass ratio in spiral. So probably this is overestimated by at least a couple of orders of magnitude. And so if I had to make a slightly more realistic guess, I would say that actually it's more like perhaps in the magnitude of 0.1 per gigaparsec cube per year. Now that probably is reasonably consistent with the kinds of analysis that happen when you try to do things in a more realistic way. So what I mean by more realistic way? Well, more realistic way, of course, relies on trying to create a detailed picture of the dynamics in the galactic center. I won't have time to go through the details of how to do that, but I will at least highlight some of the approaches just so that briefly, so that you also get an idea of some of the uncertainties. So what do you need to assume? Well, first of all, you need to assume something about the galactic center dynamics. The first thing you might actually need to assume is what is the overall distribution of stars in the galactic center. So you need to know something about the number density of stars close to the massive black hole. So as a function of the radius, the distance to the massive black hole. So for example, is it something like an isothermal distribution, 1 over r squared? Is it a Bacall-Wolf cusp, 1 over r to the 7 quarters? Is it something else again? This is a question. And of course, what is the prefactor here is also a question. Okay, we do know something about this because we can see some galaxies like our own. And so we know, for example, that in our own galaxy, that central density is approaching perhaps 10 to the 6 objects per cubic parsec. But again, this is an, the question is how true is that for other galaxies, especially galaxies with lighter black holes? So that's one question. Question number 2 is, how much mass segregation is there? So in general, the idea behind mass segregation is more massive things tend to sink towards the center of dynamical multi-body systems. It's a kind of a simple thing to understand, because if you think about it, if you imagine that there is some kind of an energy equipartition, because you have all sorts of collisions, right? You can think of it in statistical mechanical terms, basically, when you think about all these little objects, stars and so on, flying around, interacting with each other, bouncing off each other. Of course, they're bouncing off. It's not a physical bouncing off like atoms in this room, but it's more like gravitational interactions, but that also lead to exchanges of energy. And so you can really think of it as gravitational interactions having a sort of gravitational gas of particles, where the particles are your stars and your white dwarfs and your black holes and your neutron stars. Now, as with any gas, if things interact enough, they tend to thermalize, right? If I look around the room, of course, I cannot see the individual atoms, but all the atoms in this room have roughly the same temperature. So same temperature, when we're talking about objects moving around, means same kinetic energy. But same kinetic energy, if I have heavy particles and light particles, means that the heavy particles are going to have lower velocities. Now, things with lower velocities tend to sink, right? If I have some dynamical region, like a cluster of stars, if things are slowing down, right, the only way that you can slow down to 0 speed is to just sit there at the center. Otherwise, you have to be bouncing around. So that means that the more massive things slow down and sink towards the center. So that's what mass segregation is. Mass segregation is important because we want those massive things like the black holes to mass segregate towards the center, because otherwise black holes are very rare, right? Only about 1 in every few thousand stars actually has a mass high enough to make a black hole. You need a star to start out at about 20 solar masses to make a black hole. Anything less massive will end its life as a neutron star or white dwarf. So that means that black holes are rare, but if you want the most powerful extreme mass ratio inspirals, of course, the amplitude will be highest when the inspiraling object is a black hole of 10 or even a few tens of solar masses, rather than a light puny neutron star or an even punier white dwarf. So you want those black holes there to have lots of MREs that are detectable, but of course, that means you're relying on mass segregation to increase the fraction of black holes in the central regions from 1 in a couple thousand to some much higher fraction. But it's actually not clear exactly how well mass segregation is operating here, because the story I just told you, while absolutely true for something like a globular cluster, is a little bit different in the galactic center, because you have this big massive thing, the massive black hole, which is dominating the central potential, and so things get a little bit messier there. And so the exact efficiency of mass segregation, the exact ratio of massive black holes, of massive stellar mass black holes relative to neutron stars, normal stars, white dwarfs, is not entirely clear. Another thing that you have to think about is how do you actually get those compact objects close enough, or those stars close enough to the massive black hole? There are many ways of doing that. One is that you might say, well, consider this massive black hole over here. I'll just send some, once in a while, I'll just send some star on some trajectory that, normally the stars are flying around at random, right? They're scattering off each other, there's some scattering event, and the star gets close enough to a massive black hole and it just gets directly captured. This little black hole gets close enough to a massive black hole and gets directly captured. What I mean by direct capture, I mean that it was moving along on a hyperbolic orbit. Maybe its velocity was whatever the velocity dispersion is in the galactic center, and then it comes close enough at periapsis that it emits enough gravitational waves during the single periapsis passage that it loses enough energy and it goes from a hyperbolic orbit to a bound orbit. That's actually not that easy to do because the velocity dispersion in typical galactic center is something like 500 kilometers per second. That means these little black holes have quite a bit of kinetic energy. And so they would have to get really close to the massive black hole to lose enough energy to be captured. So that's not so easy. But maybe there are other ways of doing it. Maybe what you do instead is you have two black holes that are actually orbiting each other. So there are two stellar mass black holes in a binary that are already orbiting each other. And then this binary gets scattered towards the massive black hole. And then just like earlier, I did a derivation for when a star gets tidally disrupted. You can also say when a binary gets tidally separated. And again, you will find that the radius of the tidal separation, meaning how close this binary needs to get to the massive black hole to be tidally separated, this is approximately the radius of the binary, I'll call it A, the separation of the binary, times the cube root of the ratio of the mass of the black hole to the mass of the binary. So this is to the 1/3 power. And okay, this actually is not necessarily a particularly small number because so that might make it easier for you to capture one star and then the other one just gets ejected as a hypervelocity star, or in this case, a hypervelocity stellar mass black hole. It was really a black hole binary. But of course, we also don't know exactly how many stellar mass binaries there are in the galactic center close enough to the massive black holes. Also, you have to worry about things like how quickly do such objects get scattered into the vicinity of the massive black hole. So you have to worry about what's called relaxation. Relaxation is basically here, typically refers to the scattering of objects into the vicinity of the massive black hole into a region from which the binaries can be tidally disrupted, or a black hole can be directly captured by gravitational wave emission. Now, how does relaxation happen? Well, okay, there's just the regular two-body relaxation where your little star, your little binary, comes too close to colliding with another object, and that scatters it. Usually, those interactions change the angular momentum more than the energy, but that's fine for us. Even if this was a previously bound star or binary on a wide circular orbit around the massive black hole, if it gets scattered onto a low angular momentum near the radial orbit, then interactions can happen, things get exciting. So, two-body relaxations are fine, but they're actually kind of slow. It takes a long time to relax that way. So you might rely on other kinds of relaxations. There are things called resonant relaxations or even vector resonant relaxations that have to do with the presence of a, rather than a ball of stars against which you're relaxing, you might, if you have a disk of stars, and we know, for example, that in our own galactic center, there does seem to be a disk of stars. A disk is much more efficient at relaxation than a random ball of stars. It sort of already has a preferred angular momentum and therefore can exert a coherent torque rather than a random torque in changing the angular momentum of other stars. You can think of a disk of stars as kind of a wire loop that's constantly torquing other stellar orbits. So that can be more efficient, but of course we don't know what fraction of other galaxies host stellar disks. So again, that's a open question. And then there's a question of something about related to the size. Well, in a sense, both of these are related to the size and the rate of refilling the loss cone. So the loss cone is a name for the part of the phase space. You can think of it as essentially the angular momentum space relative to the massive black hole, in which things of interest are happening. So, for example, things of interest are you're able to take little black holes that fall into the lost cone, and once they get close enough, they get directly captured through gravitational emission, and then they quickly spiral in and disappear because they merge through MREs with the massive black hole. So that's a way of getting things out of the lost cone. And you want to know the rate of replenishing the lost cone through processes such as relaxation, because together the rate of removing things from the lost cone and the rate of refilling the lost cone are actually telling you what the rate of extreme mass ratio in spirals would be in this case. So you can see that things are getting awfully messy, and there are lots of question marks here. So there's a question mark around mass segregation. There's a question mark about what it is exactly that is the process of capturing things directly onto extreme mass ratio in spirals. There are questions about how efficient relaxation is. Are there disks? Is there a resonant relaxation? And therefore the rate of refilling the lost cone. And so all of these things combined mean that there are lots of uncertainties in terms of actual rate estimates. And so you can look at some more detailed calculations. So there's, for example, there are some nice reviews by John Guerre et al. There is a review from 2007 by Pao Amarusoane et al. Oh, writing Pao's name will be interesting, whether I can spell it correctly. This may be embarrassing. Pao has a lot of vowels. I hope I spelled it correctly. This is around 2007. So I think I was actually a co-author on this one. And this is a significant fraction of this review is about, sorry, that was an S, is about indeed some of the mechanisms for forming extreme mass ratio in spirals and estimating their rates. Of course, there are also more recent papers on this, but I think fundamentally, many of the challenges have remained the same. Many of the uncertainties have remained the same. And so I think we are still struggling to get precise estimates. I think if you're interested in this stuff, I certainly encourage you to read some of these papers because you will understand in more detail some of the physics I just discussed very briefly. But if you're just interested in the total rates, then something like this very crude estimate is perhaps within an order of magnitude or two is really maybe all that you really care about and all that you can confidently predict anyway. Questions? All right, let me clear this then. And let me also ask how much time do I have? Because I can stop at any point or I can do some more stuff. Just tell me for how long you want me to go on.
I mean, you have 1 hour and you started maybe 10 minutes late, so you still have 15 minutes. But I leave it to you.
Okay, well, let me do a little bit more then. I feel we should do a little bit more math. After all, this is meant to be a whiteboard calculation, so it's always healthy to do a little bit of mathematics. So let me do something which is actually going to be relevant for any binaries, MREs or stellar mass binaries, and that is to try to understand a little bit about their rate of in-spiral. And this is going to be very relevant if you want to, for example, remember I made earlier on this comment that MREs spiral in much more slowly than comparable mass binaries. So let me try to explain what I mean by this. So, okay, first of all, water-pole formula. I'm certainly not going to derive this. There's actually a nice explanation for why it's the mass. It's a time-varying mass quadrupole that is responsible for seeding gravitational waves in, for example, Bernard Schutz's paper from 84, 86. I can't remember the year, but where he does sort of a back of the envelope derivation. So he makes this nice argument that you can't vary the mass or the mass dipole because of conservation of momentum and, well, conservation of mass and conservation of momentum. And so the time varying mass protocol is actually the lowest order term you can have. So this is our gravitational waveform. So Q is the mass quadrupole moment. Two derivatives, time derivatives here. D is, of course, the distance. Now, mass quadrupole moment for an extreme mass ratio in spiral is just little m, the mass of the object, times r squared, where r is the distance to the massive black hole. Each time derivative just corresponds to a multiplication by frequency, because when you're moving for simplicity in a circular orbit, although of course MREs don't need to be circular, they in fact start out eccentric, although gradually circularize. But let's just write it as a frequency squared for the time derivative. Now, in fact, for the frequency, I can remember that my frequency scales as Keplerian orbital frequency scales as root m over r cubed. So if I plug that in for frequency squared, I end up with little m r squared, big M over r cubed over d, or little m, big M over r over d. Now, this actually is true regardless of whether you're dealing with an MRE or not. Given that we're within factors of order unity here, if you replace these masses, the two masses, one is small, one is large, by two equal masses, it'll still be roughly right. Now, I should also say I'm intentionally ignoring factors of G and C here. So G equals 1, C equals 1. Of course, if you want to get H, which is dimensionless, you look at this and you have mass squared and you have distance squared. You have to remember that you need to multiply all of your masses by G over C squared in order to convert them into units of distance. But then this is actually a nice thing to remember. This is a good way to estimate what your signal might be. So by the way, this is a way that you might also say, if you wanted to know how far away can you see an extreme mass ratio in spiral, just remember that we can sort of figure out what the waveform amplitude would be, put in the appropriate masses. For the separation, might as well put in something like the ISCO separation. So actually the separation is just 6m. And so now you just have little mass divided by 6 and divided by the distance to the source. And that tells you that you're looking at a few gigaparsecs at which you can realistically see these MREs. So a few gigaparsecs, remember, if we said the rate is something like 0.1 per cubic gigaparsec per year, the volume within a few gigaparsecs is maybe 100 cubic gigaparsecs. And so I multiply a few if I cube a few gigaparsecs and multiply it by 4/3 pi. And so then I convince myself very quickly that maybe I'm sensitive to of order 10 extreme mass ratio in spirals per year. So that's the kind of detection rate that we might be looking at with LISA if really it is sensitive out to a few gigaparsecs for these kinds of MREs. But that's actually not where I was going with this. Where I'm going with this is the following. I want to compute the flux. So this is the energy flux in these gravitational waves. Now, you can compute I won't derive this, but if you have a scalar field and you try to compute the stress energy tensor of a scalar field, and you ask yourself, which you can think of H as basically being a scalar field here, ignore the fact that it actually is a perturbation to the background space-time itself. Just think of it as any other kind of field sitting on top of a space-time. You can linearize things because we're assuming that H is small relative to the background curvature. And so that means that the flux in the scalar field just goes H squared times F squared. So if I do this, I have little m squared, big M squared over r squared, d squared. Oh, wait, I've forgotten that I have a frequency squared, which I said is itself m over r cubed. And so I have little m squared, big M cubed over r to the 5th d squared. Oh, that was meant to be a d. Clearly that my handwriting could be improved. Let me see if I can turn it into I want to draw. Why is it not letting me draw? I don't want to erase. I want to draw. No. Hold on. I'm sorry. Draw, not erase. Draw. Okay, good. D squared. Okay, that's the energy flux. Of course, you know, this is an energy flux past an observer at distance d. So the rate of energy loss, E dot in gravitational waves, is the energy flux times 4 pi d squared, because 4 pi d squared is the surface at distance d, because I'm interested in how much energy is getting out through some imaginary Gaussian surface at distance d. Now I'm ignoring 4 pi because I'm just looking at scalings. I'm not really interested in factors of order unity. And of course, okay, d cancels. So this is going to scale as m squared, little m squared, big M cubed over r to the 5th. By the way, for people who may be curious, the reason this little m squared, big M cubed is exactly where the chirp mass is coming from. If you can alternatively write this down as the chirp mass to the 5th power. So this is really why, for people who are interested in sort of compact binaries and LIGO sources, you often hear people talk about chirp masses rather than total masses, etc. It's because if we do this carefully, you end up with a chirp mass to the 5th power sitting here. So it's just a chirp mass that's relevant for the rate of energy loss. Okay, that was a little bit of an aside. The point is, this thing, the rate of energy loss in gravitational waves, has to also be equal to the rate of energy change in the orbit. Now, what I mean by rate of energy change in the orbit? Well, I have an orbital energy. This is just, again, ignore GR. This is Keplerian orbital energy. Keplerian orbital energy is G, which I'm going to ignore because I've ignored G elsewhere, times one mass times another mass, divided by, okay, technically it's divided by 2 times the separation, and with a minus sign, but I'm ignoring the minus sign, and I'm ignoring the factor of 2. So this is just the orbital energy. Sorry, this is a big mass, this is a small mass. And so E dot orb, then, if I plug this in, scales as, okay, the masses are constant. So I have big M, little m, divided by r squared, and of course, times the derivative of the radius. So now, by setting these two things equal to each other, I can immediately write down what is r dot. So r dot is equal to, well, tildes. Okay, I have little m, big M squared, divided by little r cubed. Now, this is actually a very useful statement because what I can, okay, first of all, I should always do a check. And how do I know this is actually right? Well, I don't know that it's right, but I know the units at least are right, because r dot has to be dimensionless in my units where g equals c equals 1, because r dot is the rate of change of radius with respect to time. And when g equals c equals 1, mass and time and distance all have the same units. So on the left-hand side, r dot is distance over time, that's dimensionless. On the right-hand side, I have mass cubed over distance cubed, that's dimensionless. So I'm good. It may be more useful to think about, let me define x as just a definition, as r over r ISCO. The reason I'm defining it this way is sort of I want a dimensionless radius, in units of ISCO. And so remember that if I'm dividing by an ISCO, that just means like I'm dividing by big M. So, well, 6 times big M, but this means I have little m, big M over r cubed. And again, okay, so this is little m, big M over r cubed. And sorry, this is x dot ISCO. I should be more careful. Sorry, x, let me erase this, apologies. So this is, what I wrote over here was x, and so that means that if I now write down x dot, then I end up with little m big M over r squared. R ISCO squared. If I'm evaluating x dot at the ISCO, so when I'm close to the ISCO, how rapidly is my orbit evolving? Well, it's evolving as little m big M over r ISCO squared. Now remember, this again is m squared, so I can just write this as little m over big M. So that means that at the time that I'm close to the ISCO, my halving time for the radius, my time scale for the inspiral. So the time scale for the inspiral is the time scale by which my radius, drops by a factor of 2 or changes by order of itself. That's 1 over x dot, and that is big M over little m. So that means that if I have comparable masses, then actually my dimensionless time scale. Now this is really meant to be read off in units of the orbital time. So in units of the orbital time, I am spiraling in almost dynamically if my masses were comparable, meaning that I am appreciably, by the time I'm close to the ISCO, I am, I should really put in a p orb over here. I'm changing for every orbit. I'm significantly changing my separation. But if I am in this extreme mass ratio regime, then I have this extra prefactor of about 1 million. And so that means it's taking me something like 1 million orbits or several millions of orbits to go from, let's say, a separation of 7 GM over c squared down to 6 GM over c squared. So this inspiral is very slow. In practical terms, that means that this last halving and radius might take something like multiple months, a year. In physical terms, in the terms that we're talking about here, though, we're really talking about the fact that we have 10 to the 5 cycles perhaps in this regime. And so this is why MRIs are so exciting, because MRIs are giving us an opportunity, for example, to really finely probe the space-time of the massive object. We're like we almost have a test particle that's really exploring the metric very close in the vicinity of the massive object, and is providing us through the gravitational wave signature a wonderful evidence of what the space-time is like. So MRIs are really great for doing things like probing the space-time of massive black holes, checking whether these really are Kerr black holes, or whether there are some deviations from the space-time metric relative to what you'd expect for a Kerr black hole. Okay, I think I'm really now running out of time, except to say just one last thing, that if we really plug in meaningful values over here, we find that the gravitational wave energy, we can actually do a little calculation by replacing these, by putting in the right factors of G's and C's, and we find that for a 1 million solar mass black hole and a 10 solar mass compact object, we're getting a total energy output of perhaps 10 to the 54 ergs. Remember that a beta, which is the energy unit for supernova, is 10 to the 51 ergs. So this is 1,000 supernovas. So a single MRI is worth 1,000 supernova. Another way to put this into perspective is that the energy flux is about 10 to the 47 ergs per second. Again, the typical Eddington limit, the highest luminosity you can get from this black hole, if it's, for example, accreting as an AGN, is about 10 to the 43 ergs per second. And the typical luminosities you get from tidal disruption events are sort of at that level or even lower. So this means that this is outshining in gravitational waves things like tidal disruption events or AGNs by about 4 orders of magnitude. So these are MRIs are really exciting and really fun. And I think I'll end on that. Thank you.
Thank you very much, Ilya. I think this was a very fascinating talk to see how much information you can get out by really doing simple arguments and back of the envelope calculations. I think that was masterful. Okay, so we have a little bit time for questions before we go to the lunch break. Are there any questions? If there are, then speak up or put them in the chats.
Sounds like everybody's ready for lunch.
That's what it sounds like. It's the sound of hunger. All right, so if there are no questions, then I'll suggest we stop here, we break for lunch. Unfortunately, everybody